Hello everybody and welcome to session number 19 of my lecture on statistical energy analysis and hybrid methods. Today we come to the heart of random subsystem description or SEA subsystem description because we see how a random subsystem is described, what figures are required to describe the power flow in a single subsystem, but also how the power is exchanged between the different subsystems. And this is the baseline for our final modeling of a network of random subsystems. Let's start with the global description. So first of all, we take the very simple case. We take a single SEA subsystem. This is described by very few properties that characterize the random field that is inside the subsystem. And for this, we need just some geometrical entities like the volume, the area, and the length of this subsystem. We need some dynamic properties, so the modal density, as shown in all the system description before, the damping loss, and the modal overlap. This allows us to estimate what are the properties of this wave field and if it can be assumed as a diffuse random wave field. The power input into the system for any source is given by the free field impedance, as mentioned in all the discussions before. The main parameter here is the modal overlap. So when I'm just exciting a random subsystem, it behaves, especially in the ensemble average, like the free field. So a source here in a random subsystem does not see all the other boundaries. It just behaves as a free field. So in the random subsystem, we have some dissipation, and this is the energy that is that's lost by this single subsystem description. And this expression is just given by the damping loss factor, frequency, and energy of the system. So in the most simple power balance is just the balance of the input power and the outlet power, so the dissipated power. And if we just set up this equation, we are more or less done. We have to determine the input power, and then we get the energy of this subsystem. So, this finally determines the pressure, the displacement, or the wave amplitude, because we have a relationship of the energy and the physical unit. Good. So what happens if an SEA subsystem is connected to another one? Then we would have an exchange of energy, power flow. And this power flow would be given by, let's say here, so the power flow from the subsystem number 1 is given by the energy 1, by the frequency, and the so-called coupling loss factor. Why is it chosen in such a way? Because that's a similar way as the damping loss factor, which is the similar expression. So this is a power flow from 1 to 2. The same will be on the reverse. So we will have a power flow from subsystem number 2 to back to subsystem number 1, and this will be described by a so-called coupling loss factor with index 2, 1 for the other direction. So we call this coupling loss factor because this is in accordance with the loss factor, which was defined in such a way, and that's the dissipated power. So let's have a look at the total balance for subsystem number 1. The power input is given by the above arrow. That's just the input power, and this is balanced to the dissipated power given by this expression. When we exchange system number 1, exchange energy to the other subsystem, that is given by this power flow, by this arrow here, and given by coupling loss factor 1, 2. But on top of that, there is a power input still coming from subsystem number 2, and this is given by the second expression, again using this coupling loss factor 2, 2, 1. The same can be done for the second subsystem, and this would give us this equation here. When we formulate this equation for completely for n subsystems, this power balance would look like this. So this is the dissipated power, and this is a combination of all the power that is leaving the subsystem, but that also that is coming from all the other contacted subsystem and leaving an additional power flow back into our subsystem. This is quite unhandy to let's say to understand. We can write this in matrix form. That is quite better to understand. So this is the vector of all the subsystem energies. This is the vector of all the exciting power inputs from the outside. And this is the matrix that describes this power flow multiplied by the angular frequency. Here in this term, these are all the terms that defines the energy or the power that is leaving the subsystem. And the rest here on the line, or the triangular terms, they define all the power output that is coming back to the subsystem. So the input from the neighboring subsystems. We can write this in short form. So this is often denoted by matrix L. And this is called the power flow or SEA matrix that describes our power flow between, or the energy exchange of our complex network of a global SEA model. So, but normally there is a different version used for this. If you keep in mind, there's a so-called reciprocity relationship that is valid. So just imagine that we have a plate that is excited here at this position, and we get a velocity response on the other side. And this is exactly the same like exciting the same point here and taking the response at the same position number one. This is a so-called reciprocity relationship. It relates quantities that are power related. So as you know, force times velocity is a power expression. So then have a look at our two-system SEA configuration. So the force that exciting system number one leads to an energy in system number two, and this can be reformulated in this way. So this is just a solution of the 2D matrix equation on the last slide. So we can do, and this is the same formulation can be done for subsystem excitation of subsystem number two, which would lead to this equation here. So that means, what is the task here? We have to convert this reciprocity relationship into energy terms. And the energy of the subsystem is given by the total mass and the average velocity of the subsystem. So, and if we can replace it by this expression, and the power input is given by the susceptance G and the square of the force input. And if we do so, we can modify this relationship a little bit. So that means we're now expressing the expressions before by these new formulations, and that we get this expression here, M1 to G2. And that means that now that this expression relates the SEA matrix using the conductance and the Morse quantities. So that means our force relationship is now given by this expression here. So we know from equation 202 that there is quite a simple expression for this conductance, which is just given by the modal density and the mass. And this leads finally to, if we use this here in the equation above, this leads to the so-called and very important reciprocity relationship of SEA. So that is nothing else than, let's say, a translation of the classical reciprocity relationship into an energy and power reciprocity. And this means that the coupling loss factor 1 to 2 multiplied by the modal density 1 is the same as 1 to the modal density of 2. And that means that we can simplify our matrix. So we are, let's say, we take the same energy value, but now we divide this energy terms by the modal density, the related modal density. And this leads to the fact that in our matrix formulation, we have always combined terms of modal density by a coupling loss factor. And if you keep in mind, those are related by the so-called reciprocity relationship. And that's a good thing, because that means this new matrix is symmetric now in this formulation. And this is much better suited for computational efficient solvers. So we all know that the symmetric matrix is much easier to solve. This is one advantage. Another advantage is sometimes it's hard to calculate the coupling loss factor from 2 to 1, and it's much easier to calculate the coupling loss factor to 1 to 2, and then we have a choice. We just take the simpler version, and we can, let's say, calculate the 1 to 2 by using the different modal densities. So there are several reasons why this symmetric version should be used. And this is just called L prime, and this is called the symmetric power flow or SA matrix. And this is what you're usually using in the literature and also in commercial packages. Okay, so far for that. Now it's time for a nice analogy that is very often used in SEA books, literature, and presentation, the so-called fluid analogy. It is sometimes quite helpful because it can visualize the exchange of energy and whatever of a typical SEA subsystems. And here the modal density corresponds in this analogy to the width of the tank or of the take. So this is given here, but denoted by those arrows. The energy is the volume of the water, so that means that the relative modal density, also the energy per modal density, is the height of our water tank. The power input, that's clear, that's the volume that's flowing in per time, obviously, and the dissipated power is the volume that is flowing out. What I don't like that much with this model is it slightly fades in case of losses in the coupling, because the dissipated power would depend on the height and not in terms of the energy, because the height is defining the pressure, and that's how much water would leave this tank. And the same is also true for the coupling loss factor. So the amount of energy that's flowing here would, in a classical hydraulic system, would depend on the pressure or the height of this water column, and this is the energy per modal density, and this is not correct, because the coupling loss factor is related to the energy. This is the slight point where this model fades. There's no big damage because no one is using this for calculating SEA. However, I would just like to mention it because it's very often used. Good. Once we have calculated the energy, we have to keep in mind that we have to get back to our, let's say, acoustics or vibration-related quantities. This is given, for instance, by the pressure, by this relationship between energy, volume, and the group velocity. This gives all the normal speed of sound. That gives us the pressure in the subsystem. And for plates, for instance, it's the displacement, or it could be the velocity. This is related by this relationship. For practical reasons, it's very often let's say structural solutions are given as velocity or accelerations, but that's not a big deal, because by scaling it or multiplying, dividing it by omega, all those expressions can be derived from the displacement and or velocity, acceleration, vice versa. So that's it. That means this is all we need to create an SEA subsystem. An important quantity and the important dynamic quantity is the modal density, as I've mentioned already. We have learned a lot of formulas that are used to calculate the modal density or to estimate it. It's for one-dimensional system, it's mainly determined of the length and the group velocity. For two-dimensional systems, it's given by this expression here. And for cavities, which are mostly rooms for practical reasons, is given by this. So perfect room would be sufficient to use this expression, and those are the corrections that you need if you have a flat or long or whatever, some kind of disturbed cavity shape. Good. So also very important is the criteria for a random subsystem, and here the so-called Helmholtz number is quite important, because that's the ratio of the dimension of a subsystem to the wavelength. And just to give you a very rough feeling, you should be greater than 10. If there are less than 10 wavelengths fitting into our subsystem, you should not even think about using SEA. Another very important criteria is the modal overlap, because the modal overlap defines if the free field assumption is correct, so that the input power can be derived just by assuming a free field impedance or a free field radiation stiffness. When we check the modal density, or when we express the modal density in terms of the Helmholtz number, we also understand why systems of higher dimension become random much earlier or easier in frequency. It's clear because the modal density here, it's a square of the Helmholtz number, and here it's a cube of the Helmholtz number. So that means with higher frequencies, the system becomes much earlier random than the one-dimensional case. So this is also the reason why in classical SEA calculations you use normally two-dimensional and three-dimensional subsystems as SEA subsystem, and rarely a one-dimensional subsystem. Good. So that's for the first introduction of, let's say, the power flow matrices of SEA subsystem. Thank you so much for this very first and very important session for really dealing with an SEA subject. And the next session will be about the coupling. And we start with how to formulate the coupling, how deterministic, random, or deterministic and random subsystem are coupled. And this is the first step that we need to calculate coupling loss factors. So how we really get the data that we need to understand what is this eta 1, 2 exchanging the energy between subsystem number 1 and subsystem 2. That's a very important thing, because in many other books this is just omitted, because that's a complicated part. And with the help of this diffuse field reciprocity relationship and the hybrid theory, okay, it's still complicated, but it's much more straightforward and much logic as in the classical and old literature. And hopefully, and this, by the way, was the idea of my book, to use this foundation of SEA to much better explain all the coupling loss expressions. Have fun, and see you then for the next session.